Let us now discuss a very important topic, and that is active high and active low inputs or outputs. And we will discuss this topic in the context of multiplexers, but we should remember that this is very general terminology, and in fact we will see this in several other digital circuits as well. Alright, so here is a multiplexer with this truth table here. In this case, the select inputs are active high. That means if this S0 is a high voltage, then it is considered to be 1. If it is low, such as 0 volts, then it is considered to be 0, and so on. And the functionality is then described by this table. Let us consider this second example, in which the select inputs are active low and they are denoted by S1 bar and S0 bar rather than S1 and S0 here. Now if S0 bar is 0 or low, then it is considered to be active. So for example, if S0 bar is 0 here, that corresponds to S0 equal to 1 in this table, and similarly for S1 bar. If S0 bar is 1, then that corresponds to S0 equal to 0 in this table. So in other words, this second table is obtained from the first table by simply inverting all of these entries. So that is how this active high and active low terminology works. Let us now discuss something called the enable pin, which is very common in digital circuits. Here is an example. We have an IC with some inputs and some outputs, and then there is this pin called the enable pin, or E. In this case, it is an active high enable pin. Let us see how it works. If the enable pin is active, the IC functions as desired. For example, if this is a multiplexer and this enable pin is 1, then this IC will actually function as multiplexer. If the enable pin is low, then the IC is disabled. That means the outputs are set to some default values. So in order to make the IC work as desired, we need to make the enable pin active. The enable pin can be active high or active low. In this case it is active high, and here is an example where the enable pin is active low, and that is why it is denoted by E bar. If the enable pin is active low, it is denoted by enable bar or E bar, and in that case when E bar is 0, that is active, the IC functions normally, else it is disabled. That means the outputs will be set to some default values. Let us now take up this problem in which we have two 8-to-1 multiplexers and we want to make up a 16-to-1 multiplexer using these two. So here is the 8-to-1 MUX 74151. It has got 8 input lines I0 to I7, 3 select lines S2, S1, S0, and it also has an enable pin, and this enable pin is active low. That is why it is denoted by E bar. So we have two of these, and using these two we want to make up a 16-to-1 multiplexer. So let us see how to go about doing that. So here is the truth table that we expect from our 16-to-1 multiplexer. These are the select lines and that is the output. So this entire box is supposed to function as the 16-to-1 multiplexer. These are the input lines from D0 to D15. These are the select lines S3, S2, S1, S0, and that is the output X. When S3, S2, S1, S0 is 0, 0, 0, 0, we would like X to be D0. When these are 0, 0, 0, 1, then we want X to be D1, and so on, all the way up to 1, 1, 1, 1. In that case, we want X to be D15. What we can do is split this functionality into two parts. We can implement this first part with 1 mux, 1 8 to 1 mux, and the second part with a second 8 to 1 mux. And we note that this select line S3 is 0 for these first 8 entries, and it is 1 for these second 8 entries. And that is something that we can use to enable either the first multiplexer, this one, or the second multiplexer, this one. And that is what we have done in this implementation. S3 here is connected as E bar of the first mux, and S3 bar is connected as E bar of the second mux. When S3 is 0, then this mux is enabled. It works as a multiplexer. This mux is not enabled. So we get x2 equal to 0, and the output is the OR of x1 and 0, that is x is equal to x1 in that case. Now when S3 is equal to 1, then this IC is enabled. It works as a multiplexer. This one is not enabled, so x1 is made equal to 0, and the output is the OR of x2 and 0, that is x becomes equal to x2. What we will do now is to consider two cases, one corresponding to this first part of the table, and second to this second part of the table. And in each case we will verify whether this output x is what we would expect from this truth table. Alright, let us take this case first, in which S3 is 0, S2 is 0, S1 is 1, and S0 is 1. So if those are the inputs applied here, we expect D3 at the output, and let us see if that happens. Since S3 is 0, this mux is enabled, this mux is not enabled, so this x2 is made equal to 0, and our x is equal to x1, as we have seen before. Now what are the select lines for this first mux? S2, S1, S0, that is 0, 1, 1. So we have 0, 1, 1 here, that is decimal 3. That means this line I3 gets connected to Z here. And what is line I3? Line I3 is the same as D3, so that D3 gets connected to Z. So our x1 is equal to D3, and therefore x, which is equal to x1, is also equal to D3. So we do have then the expected output in this case. Let us now pick one case from the second part of the table. Let's say this one. So what is S3? S3 is 1. So this IC is enabled, this one is not enabled, and x is equal to x2. Alright. And what are S2, S1, S0? We have 1, 1, 0. So this IC gets 1, 1, 0. 1, 1, 0 is decimal 6, and therefore this line I6 will get connected to Z. What is I6? Let us look at that. I6 is the same as T14. So therefore x2 and also x will be equal to D14, and that is what we would expect. So this whole implementation works as a 16:1 multiplexer.